So we are now recording, and again, I'm sure as usual there'll be a few more. We'll join in here in the next few minutes. Running a little bit late this morning for some, but that's okay. Remind everybody. Mentioned this yesterday, but nothing has changed since yesterday. As of right now, our first test will be Monday. This coming Monday, I think it's the 15th. And it will be at 11 a.m. So you'll take your test during our regular scheduled class time. Focus. And there we go. So yesterday after class, sometime in the afternoon, I sent out a couple of emails. One had some information regarding HonorLock. Well, we are using HonorLock to proctor the test. And then the second email had kind of an outline of a step-by-step process of how exactly the test was going to be conducted or administered. So before we get started today, forging into some new material, I'll take a few minutes. Hopefully everybody did like I asked and actually read the emails I sent out. And now's your chance if there was any questions you have, something in the email that didn't make sense to you or whatever. Now would be the time to speak up and voice those questions, or you can type it out in chat. I did.
So,
Go ahead.
so how early would you open up the test? Like before, like 15 minutes or 5 minutes before? Because I know working with it, it can take a bit to try to get your ID scan and
Yeah,
all
well,
that.
that's why I said in the email. If you want to, go ahead and start the process a little before 11. That's fine. It should be that you get 60 minutes from after you get through the HonorLock verification. You should get 60 minutes from when you actually access the test and start taking it. But I don't know if you've got something else, scheduled. You got to be somewhere at 12. Then in that case, definitely you might want to start, say, I don't know, 10:45 or so. Start, logging in, however long it takes you to get through the HonorLock verification. That would be up to you. But whenever you get through that, you still should have 60 minutes to take the test. Okay? Does that make sense?
Yeah. Thank you.
So sort of up to you. If you want to make sure you're done by 12, start about a quarter till,
Right.
something like that.
Okay. Thank you.
You're welcome. So good question. Any others? Again, I apologize. The emails were long yesterday, but maybe I did a good enough job. I tried to explain in great detail. So maybe by the lack of question means I did a pretty good job of explaining how it was going to work, or a bunch of you didn't take the time to read the email. Hopefully it was the former, and not the latter. All right, so last chance. Again, if you think of something, question-wise regarding the test between now and then, don't hesitate. Ask me later this week, and we'll talk some more specifics about the test on Friday this week. We'll take about half the class, kind of a sort of review what you're responsible for on the test. We'll do that Friday. So today we're going to kind of change gears a little bit from what we've been doing. Pretty much all of chapter 1 dealt with stresses. And what we're going to introduced in chapter 2 has more to do with deformation. You have forces, moments acting on different types of structures. It's going to cause what we've learned so far, normal stress and shear stress. But it's also going to cause the object to deform or change shape. And that's kind of the focus here in chapter 2, which has got to be one of the shortest chapters probably in any textbook I've ever seen. It's a really, really short section, kind of introduction. And then there's really only one section with stuff in it, and that's section 2.2. And we're going to define what we mean by strain. And this is it. This is all of chapter 2. So we're going to do this today, and then we'll have time. I'm pretty confident. In chapter 3, we'll get into a little more about material properties, and we'll start talking about that today. Continue it the next couple of days. But let's start with what we define as strain to be. We find stress as force per area. Well, just like we had normal stress and we had shear stress, we're going to have normal strain and we're going to have shear strain. And like before, part of I don't know if I would call it a challenge or not, but is learning the notation and terminology. Normal stress, we use a lowercase sigma. For normal strain, we are going to use another Greek letter, lowercase epsilon. And my epsilons probably don't look a whole lot like the epsilons you'll see in the book, but just be aware. That's the notation we're going to use to define normal strain. And basically what normal strain is, it's a change in length over the undeformed length. So it's a ratio of how much the object deforms divided by its original undeformed length. So a classic illustration here, if you've got some bar with some length L, and this would be the undeformed position. So L we're going to denote as the undeformed length. And then if something causes this thing to change length, and just for this illustration, we'll show it getting longer, but it could get shorter. So this deformed length, we're going to call L prime. This would be the deformed position. Now, what causes it to change length could be, a number of things. Could be, we apply an axial force and tension, and we pull and stretch this thing. We could apply an axial force and compress it, and it gets shorter. We'll see later in the textbook when we talk about the effect of temperature change. A temperature change can cause the object to change length. So what causes it to change length at this point really doesn't matter, but we're going to have some change in length we'll call delta L. Right? That would be how much it gets deformed. So based on our definition up there, our normal strain would be the change in length. So you take the deformed length minus the undeformed length and divide by the undeformed length. Or quite common, you see delta L over L used. And I don't remember if in this section you'll see this notation or not, but I know in chapter 4 you will. Instead of delta L, you'll see another Greek letter used, delta, lowercase delta over L. So it really doesn't matter, to me, what notation here you want to use. You're, calculating strain. Up to you. But I did want to point out, it's very common you'll see all three of these types of notation used. It's just the change in length over the undeformed length. Now, for units here, right, if we've got length and we're dividing by length, the units cancel out. Whatever unit of length it is going to cancel out. So technically, it is dimensionless. Oh, dimensionless. I think I spelled that right. Whereas with stress, we had force per area, PSI, or newtons per meter squared, we call pascals. Strain is just a number. Now, it is common, and you'll see this done in this textbook. Different textbooks, some do this, some don't. Out in the real world, it's actually fairly common to use something like if you're doing English units and your dimensions are in inches, you might see the strain given in inches per inch. If it's SI units, most likely probably millimeters per millimeter. And so you will see this in the textbook, but you do not have to do that for me. So on a test, if I ask you to calculate the strain, it's up to you. If you want to just give me a number, that is fine. It's not required that you put units because units cancel. But if you want to, say the strain is 0.001 inches per inch, that is fine too. That is strictly your choice, but I will not penalize you if you don't put inches per inch or millimeters per millimeter. My opinion, it's not necessary. All right, and also just like with normal stress, and we had the tension and compression, same thing applies here, right? If you stretch this thing and have elongation like I'm showing in this my picture, right? That corresponds to what we call positive strain. And you'll see, you'll get a positive number if you take if the deformed length is bigger than the undeformed length, the numerator is positive, you're going to get a positive number. Again, this corresponds to what we call tensile strain. And if you have the object get shorter, if it's short, I think that's a word. Right, so if instead of getting longer and stretched, it gets compressed, and your deformed length is shorter than your original length, you'll get a negative number in that numerator, and so you're going to get a negative strain. And again, we would refer to that as compressive strain. All right. Any questions about the definition or what we mean by normal strain? All right. And shear strain is a little bit different. It's not, shear stress is a little bit different than normal stress. So you're going to see shear strain is likewise a little bit different than normal strain. Notation wise, again, we're going through that Greek alphabet. This is a lowercase gamma, lowercase Greek letter gamma. It's what we use to denote, call shear strain. Now, where normal strain was a ratio of the change in length to original length, you're going to see shear strain a little bit different. It's an angle. It's the angle of distortion. The units here are going to be radians. It's an angle, so we could have radians, could have degrees, but it's got to be radians because just like normal strain is dimensionless, You should know, well, we call them radians. Radian is also actually a dimensionless quantity. So we might say, pi over 4 radians. But it's just a number. It's a real number. We say radians, but it's dimensionless, unlike degrees. So it's angle, distortion, which, again, if I draw a picture here, I think will help illustrate this. Let's say we've got some, here, rather than looking at, say, like a bar, if we're looking at some little element, so if we take some little cube out of this structure and we apply shear stress. Remember, shear stress acts parallel or tangential to the surface there. So if you apply this shear stress, let's see if I can get a pen, one to the top surface going to the right, and we apply a shear stress to the bottom going to the left, it's going to cause this little element to change shape. It's going to distort it. And what you're going to wind up with is a distorted element where this angle here, that is the angle of distortion. That is the angle that this element has been deformed or distorted. And that angle right there is what we define the shear strain to be. Now, there's also going to be some horizontal displacement here. I'm going to call this delta x. Now, there's a relationship between that horizontal displacement and our shear strain. If you look at our triangle here, we've got a nice right triangle. One side is the height of this thing. The other side is our horizontal, in this case, horizontal displacement. This is the first time we're going to use this small angle approximation. So this is not going to be the only time we'll use this. Some of you may have seen this before somewhere else. Others maybe not. I don't know. But this is the first time we're going to use it. If you've got a really small angle gamma here, then if it's really small, it's approximately equal to here, tangent of that angle. So you take any really small angle, and if you take tangent of that, it's going to essentially be the same as the angle itself in radians. So therefore, for our purposes here, we can make use of that small angle approximation, and we can say that the shear strain gamma here, tangent is what? Opposite over adjacent. So the opposite is the horizontal displacement, delta x, and then the adjacent side is the height L. So it is perfectly fine to use this. If you've got a similar problem, use this small angle approximation. We're going to see, if you actually deform a real structure, right? If you go back up here to the normal strain, that change in length is going to be really small. This angle is going to be really small. If you've got a really big angle, or you've got some really big change in length, you're permanently deforming the structure and maybe even breaking it. And in real world applications, you're not going to have deformations that big. You're always going to be dealing with very small deformations. So certainly make use of that relationship if you run across a similar problem. And maybe one last thing about shear strain, and then we'll see if we can work an example. And that would be sometimes, if you also had this example that I did here was showing, if we just had shear stress on the top and bottom like that. But if you also had, shear stress on these surfaces like this, it's going to cause it to, see my hands, it's going to deform this direction as well. And so if you run across, let's see if I can draw something sort of parallel here. All right, so if you see an object that is distorted or deformed in both directions here, we'll call this this angle here, gamma 1, this angle down here, gamma 2, then the actual shear strain for that would be the sum of those two angles. It would be the total. You would add them together. It would be sigma, or not sigma, gamma 1 plus gamma 2. I get my Greek alphabet right. So if it's distorted both directions, you just add the angles together. Again, in radians to get the shear strain. All right. So take a second here. If you have a question, something related to shear strain, speak up before we work a problem. All right. I'm taking silence as we can move ahead. There's several good examples in the book. As usual, it's always a good idea to look at those examples in the book. One thing you will see for the problems in this section is pretty much all just solving a geometry problem to figure out what the change in length is or what the angle is. As long as you know the definition of normal strain is change in length over length, shear strain is that angle. That's really the only mechanics and materials part we're going to see here. Calculations in the work involved is just going to be really, again, as I said a second ago, solving geometry problem, trying to calculate what these deformed lengths are. So let's see if we can do one. All right, so let's see. Let me draw a picture. We'll start with the picture. We've got this vertical member, and we have a pinch port holding this thing up down here at the bottom. And we've got a cable attached here. I think that's A. Goes up here to B. If I can draw a straight line. Yeah, this is straight across, horizontal. And we need some dimensions here. From C to B is 300 millimeters. And from B to D is the top of that. Is also 300 millimeters. From A to C, this horizontal distance, 400 millimeters. And we're going to apply a horizontal force P to the top of this vertical bar. All right, so that is, again, what the picture, I think I got all my dimensions, everything. And so we are told that when we apply this horizontal force P, oh, I did forget one thing. We're assuming that this vertical member is rigid. All right, so that means it is not going to deform. The purpose for that is, in real life, if you had a vertical member and you pulled on this thing to the right, two things would happen. One, you're going to get a force in this cable AB. We got this cable here that is not rigid. it's going to stretch. And as it stretches, it gets longer, it's going to allow this vertical member to rotate. Now, in real life, if this was not rigid, that vertical member would also bend. And we have not got to bending yet. So that's why you'll see all these similar problems like this in your book. At this point, any member that would bend, they're going to tell you it's rigid. Otherwise, you'd have to take into account the bending. We haven't covered that yet. Right. Well, so what's going to happen is this thing is going to, if it's rigid, it's going to stay straight. So I'm going to do my best here to try to draw a straight line. Right? Everybody in agreement with me? If we pull on this thing to the right, this member is going to rotate to the right. And we are told that this angle here is, we'll call it theta, is 0.3 degrees. Right? And again, that's given. Right? So we are told how far, at what angle this thing is going to rotate. And as I mentioned a minute ago, you'll see we're dealing with really small deformation. And what we are tasked to find is the normal strain and cable AB. So you go back to, our definition of normal strain is change in length divided by the original undeformed length. Well, when it's vertical, this is when it's undeformed in this position. So we need to know what is that, I'll call it LAB. That's the undeformed length. This you should be able to get just by looking at it. Now, obviously, we got a nice right triangle. We know this side's 300 millimeters. We know this side's 400 millimeters. So we could get the hypotenuse by saying 400 squared plus 300 squared and take the square root. But this is a special triangle. So if it's not a special triangle, you would have to use Pythagorean theorem to calculate that. But it's a 3, 4, 5 triangle. So I hope everybody's with me. Just by looking at it, we know the original undeformed length is 500 millimeters. Right? Anybody not see that? So this is where it becomes a geometry problem. We've got to figure out what that deformed length is. Now, part of the reason I chose to work this one is it's kind of like the small angle approximation talked about a second ago. For this particular problem, now in reality, what really happens, right, if you've got this member, this vertical member, and it rotates, about this point C down here, the end of this is going to follow a curved arc. In fact, it's going to be a circular arc, right? That's what's going to happen. It's going to move horizontally. It's also going to move down. Right? That's what's going to happen to point D here. In real world, if that bar CD is rigid, that's what's going to happen. But we're talking about very, very small, these horizontal and vertical deflections we're talking about here are going to be really small, probably almost hard to see with the naked eye. I mean, this is very much exaggerated. 0.3 degrees is nowhere near this big. But I drew it like that so we could actually see it. Same thing here. This is sort of blown up, and we're exaggerating those things. But as long as we stick with the assumption. So if we assume very small angles, which again, 0.3 degrees definitely meets that criteria, right? It's okay to assume that it moves in a straight line. In other words, we're going to assume we got CD here. Rather than moving in this curved circular path, we're going to assume that it just moves, in this case, horizontally. Right? So if you look at any point on here, we're going to assume it just moves straight across. Right? And again, as long as we got really small angles, it is valid to do this. It makes solving the problem a lot shorter and easier. And you'll see, if you went back and solved this problem and actually took this into account, which you can do, it's not that difficult, but there's more work involved. You will see out to probably about 5 or so decimal places, you're going to get the exact same answer. It's not going to matter. Now, if this angle was 30 degrees instead of 0.3 degrees, this would not be a valid thing to do, right? You would get a significant difference between the actual curved path and assuming it just goes straight across, right? So again, anytime you see a similar problem to this, and we'll encounter more of these later as well, we're going to do this, right? We're going to assume we got small angles and we're going to neglect the curvature. Basically, that's what we're doing. We're neglecting the curvature of the path. So with that in mind, this becomes a geometry problem, right, that we need to solve. Let's I'm going to draw a new picture down here. So we're looking at, we need to find what's the new length of AB. Right, so here is point A, and again, this is greatly exaggerated, but this thing we're going to assume goes 0.3 degrees. We're going to assume, we'll call this B prime, that it goes straight across, right? We're going back to what we talked about just a second ago. And so what we need to find is what is this length. Right, we'll call it LAB prime. Right? That's the new length of cable AB. Now I know this dimension, right, that doesn't change. It's 400 millimeters. If this bar is rigid, the distance from B to C does not change. It is 300 millimeters. So it just becomes a geometry problem to calculate what the length of AB prime is now. And there's more than one way to do this. So we could break it up into 2 right triangles and we could get there that way. Or if you notice, we've got a triangle where we know 2 sides and we know the angle between them. Right? This angle is 90.3 degrees. So this sets itself up really nice to using law of cosines, if you remember what the law of cosines is. But as I said, not necessary. You could get there by breaking it up into 2 right triangles if you don't happen to remember law of cosine. But law of cosine says the side opposite the known angle, which I call it LAB prime squared, is equal to this side squared plus that side squared. 400 squared plus 300 squared minus 2 times those 2 sides. So minus 2 times 400 times 300 times cosine of this angle between the 2 sides. So that would be times cosine of 90.3 degrees. All right. And so we saw for this new length, right? That's the length of the cable when its bar has rotated around 0.3 degrees. I got 501.255 millimeters. So now we know what the original unstretched length is. We know what the deformed length is. So to get the normal strain, again, it's just the change in length over the original length. So the change in length is 1.255 millimeters. The original length was 500. Again, millimeters. Again, those units are going to cancel. As long as the units are the same, you're fine. It doesn't matter what units they are. They're both meters, both millimeters. You're good as long as they're the same. And so you're going to get a really small number. I got 0.00251. And again, if you wanted to put millimeters per millimeter, that's fine. If you want to put no units there because it is dimensionless, that is fine too. Be careful when you're doing these strain calculations. Make sure you take out a bunch of decimal places. Wasn't necessarily really that vital when we're doing stresses, but strains, you're going to be dealing with really small numbers. So don't round it too much. Okay? So this is a typical kind of problem you're going to see in this section. You're going to have some object gets deformed. You're going to have to do some geometry and figure out what the deformed length is. Or in the case of shear strain, you might have to figure out an angle. And any questions about strain? Hang on just a second. All right, anything else about this problem or strain in general? All right, well, the last thing we're going to talk about today is what we call a stress strain diagram. So this is getting into chapter 3. This is section 3.2. Stress strain diagram. And all this is, it's a graph. And it's a graph of normal stress, sigma P over A, versus normal strain. We just saw epsilon was what, delta L over L. So how this stress strain diagram is obtained is experimentally. So what I'm thinking about, I'll mention that. So data is obtained experimentally. So somebody takes a specimen of A36 steel. I mentioned that the other day. You take a steel bar, you know the dimensions. You apply a load, you know the load. So if you know the force, you know the cross-sectional area, you know the stress. They measure how much it deforms. Well, if you know how much it deforms, you know the change in length, and you've measured the original length, you know the strain. And so it gives you a data point, and you plot that stress that corresponds to that strain. That's all this is. The shape very much is dependent on the material. So there are sources out there that have, I've got a big 3-ring binder sitting on my bookshelf that it's got all kinds of material properties in it. And for each of these materials, it shows you the stress strain diagram for that particular material. Different materials, the graph is going to be different. Now, there are some similarities depending upon what the materials are. For example, I'm going to draw an example here for, say, most, say, structural steel. You're going to get a stress strain diagram that is very similar in shape. Now, the numbers will be different. Obviously, if it's a stronger steel, it doesn't deform as much. You're going to get higher or smaller values of strain and higher values maybe for stress. Whereas if it's not as strong, you're going to get lower stress values and bigger strain numbers. It's going to deform more. But the general shape is going to be the same. And that's what we want to finish up today talking about. Is what this typical stress strain diagram looks like, and what some of these significant points on the graph entail. Now, again, this is what we're going to draw here. There's also a good example of this in the book, and I'm going to write this down so you go back, look at the picture in the book. It's going to have more detailed explanation. If I look that up, I think it's on page 88 in your book. But you're going to see a very similar diagram to what I'm going to draw here, but you'll get more details and explanation about different points on the graph. So every structural steel, it's going to start out with a linear, if I can draw a straight line here. In fact, this is, you'll see this in the picture in the textbook. This is what we call the elastic region. This is where it is linear. Initially, I better label my axes. This is strain, this is stress. No, I can't draw a sigma. Pretty much all, again, we're talking about structural steel here. When you look at the stress strain diagram, it's going to start off, the first part of it's going to be a straight line. And then it's going to start curving, sort of curve over. And then we're going to come back and talk more about these specific points in a minute. It's going to sort of curve over and sort of flatten out. It won't be completely flat, but you'll see gets a lot more horizontal. And then it will curve back up. And then somewhere out here is where the specimen would break. And so we want to define a couple of points. This one, this is what we call the proportional limit. That's what the PL stands for, proportional limit. This defines the linear part of the graph. So when you look at this stress strain diagram, the point where it stops being linear, that stress is what we call the proportional limit. Now, at that point, it's going to start to curve, and it's going to bend over, and then about where it starts to flatten back out, that stress is what we call the yield stress. And we'll come back and we'll talk about another point in between those in just a second. But for now, let's go with that. Now, at some point up here is where you're going to reach your maximum. Well, my line kind of didn't line up, but this is what we call the ultimate stress, right? This is our maximum stress. That's the maximum stress that particular material can take. At that point, when you reach this, so this is sigma PL, this is sigma yield. When you reach this point, you're not coming back. It's going to break. Now, right before it breaks, the stress actually will go down a little bit. And if I can draw a straight line over here, this is what we call the fracture stress. So this would be the fracture stress. That's the stress when the thing actually breaks. But what happens in between here and here, again, once you reach that ultimate stress, if you don't take the load off at that point, what you're going to see in here is what we call necking. And there's a good picture in your book. What you'll see is you've got a bar. You'll start to see the cross section do something like this. Right? You'll start to get smaller here. And it does that right before it actually breaks. So that's what's happening once you reach that ultimate or the maximum stress. Between there and when it actually breaks, this thing starts deforming a lot right before it, splits in two. Now, if you go to the book and read about this, you're going to see this other point here that's called the elastic limit. Now, technically, that is the point at which you would get permanent deformation. So the elastic limit is the stress at which permanent deformation occurs. Now, you don't see that term used a lot in the real world, but you will see it in your textbook. That's why I'm mentioning it now, because some of you are good and go back and read this in the book. I don't want you to get confused and come back and say, well, you said the yield stress was where you had permanent deformation, and the book says it's the elastic limit. But for most, especially most metals, this elastic limit is essentially the same thing as the yield stress. It's really, really close. Again, my picture here is showing, it's not exactly the same point. And technically, it's not exactly the same point. But they're really, really close together. So it's common to use the yield stress as the stress where we get permanent deformation. In practice, that's what's generally done, is we consider if it gets to the yield stress, we're going to have permanent deformation. So in other words, when we take that load off, it's not going to return exactly to its original undeformed shape. Everything up to that, you go, and you'll see in the real world, almost all structures are going to be in this linear region, less than the proportional limit. It's not going to experience permanent deformation. You don't want to permanently deform your structure. You want stress levels less than the yield stress. But this is a very common, prototypical shape if you look at a stress strain diagram of some steel. As I said, different steel alloys will have different values. You'll have different strain values. You'll have different numbers up here. but the general shape of the diagram will be similar to that. So we're just about out of time. Just kind of give you an idea, preview tomorrow. We'll continue talking about stress strain diagrams. In particular, we'll look at something that's not, what if you got something other than a steel? What kind of stress strain diagrams, what do they look like? We'll talk about the relationship between stress and strain. There's something called Hooke's law that gives you that relationship. And then we'll use that to solve some problems. That's where we're headed. But this is a good place to stop. We're out of time. Any questions about stress strain diagrams before we wrap this session up? Taking silence is no questions. So as usual, I'll tell you before I stop record here, if you've got a question about something else, anything else, and you want to stick around, hang around, be glad to address that on our WebEx session. But let me stop the recording, and then we'll see if anybody has anything.